Okay, so I think we can start slowly. Today we will have Frédéric Paradis, who is a PhD student with François Laviolette at the Graal. Frédéric is completing his second year as PhD student, is close to his third year, and he will present us the Poutyne, which is a framework for simplifying some boilerplate code for PyTorch. So Frédéric.
Hi, my name is Frédéric Paradis and I'm part of the Grade Research Group, and I'm going to present to you Poutyne, which is an easy and flexible deep learning framework for PyTorch that we use a lot in our lab. So what is Poutyne? As Christian just said, Poutyne is a framework for training neural network with PyTorch, and it includes checkpointing and logging mechanisms, and also other kind of mechanism that simplifies our life. And as we see, it allows to set up experiments quickly so that we don't have to always code the same thing. So here are some core principles that we applied when developing the library. First of all, we want it to be easy to use for simple use cases. So let's say you want to say train image classification network, then it's something easy, and it should be easy with Poutyne to do it. But since we're doing research, we want it to be flexible enough for more complex use cases. So for instance, training a variational autoencoder should be possible with Poutyne. And also, as we'll see, Poutyne contains a powerful mechanism of callbacks, where essentially you can do everything with callbacks in your training and evaluation loops. So here's a chart explaining a bit of the flow with Poutyne. You start with PyTorch, where PyTorch you have your PyTorch network, PyTorch optimizer, etc. And then you input this your network into the model. Model is a class in Poutyne that will do almost everything I just discussed before. And once you've done that, you can train your neural networks with the fit function by passing here the data and callbacks. So the callbacks will allow you to do early stopping, to do error scheduling, learning rate scheduling, to do checkpointing, etc. And then once you train your neural network, you can evaluate it. Poutyne contains matrix that you can use to evaluate your neural network. And then we have this big box here that I called experiment. As we see, we have an experiment class that allows you to wrap everything and do almost anything in a few lines of code. So let's start with PyTorch for those who don't know what PyTorch is. So PyTorch is an automatic differentiation framework library in Python. So essentially, in PyTorch, you define your neural network the same as in TensorFlow. For those who know TensorFlow, you define, for instance, your weight biases, and then in the forward method, you execute the operation that your neural network does. So, and then what PyTorch does is that it takes these operations and it allows to find the derivative of the gradient of the parameters to optimize the neural network automatically. So here is some example of pure PyTorch training with a neural network. So here we define the neural networks with the data, and then here are the training and validation loops. With Poutyne, what we aim to do is to arrive with some code like that. So here you might notice that the code is really nicer and smaller, but it does everything that this do. So essentially, with Poutyne, you still define your neural network with your loss function optimizer, and then you use the model class of Poutyne to input your neural network with your optimizer, with your loss function, and maybe some matrix, and then you can fit and evaluate your neural networks on your dataset. So let's talk about this model class. So the model class is actually the main class of the framework. One of the things that I find nice with the model class is that it plays well with NumPy. If you pass it NumPy arrays instead of torch tensors, Poutyne will convert these NumPy arrays into torch tensors automatically. And one other thing, to keep the framework as flexible as possible, I put no restrictions on the input or the output format of the network. That is, for instance, your network can input tuples or dictionaries of tensors or NumPy arrays, and then it can output, again, dictionaries or list of tensors or etc. So, so this allows us to do almost anything as we want, and also Poutyne will manage the devices. So let's say you want to put your network on some GPU and then train it on this GPU. Then Poutyne will transfer the neural network on the GPU, and it will transfer also the data to the GPU, each batch to the GPU that you ask. So here below, some code. As before, we initialize a model with the neural network, the optimizer, and your loss function. We send the model to some device here, and then we ask it to train from data loaders in PyTorch. They are data loaders to split data into batches. So Poutyne takes these data loaders and run for some number of epochs. And then we also pass the callbacks here that will allow us to do a lot of stuff. And then finally, we can ask Poutyne to evaluate the neural network on some test data loader. So yeah, so let's look at how we train a neural network with Poutyne. So so this is the training flow that we take with Poutyne. We start with some batch of data that we input into the neural network. The neural networks output some predictions, and then using the loss functions, we compute the loss for the prediction of the neural network, and then we do the backpropagation, following by here the optimizer step, so the update of the parameters, and then we start over with another batch. So essentially, this is the pseudocode of the training with Poutyne. So for a certain number of epoch, we draw batches from the training set. We compute the prediction of the neural network. We compute the loss for these predictions. And then we compute the gradient for the parameters of the neural networks. And then we update the parameters with the optimizer, for instance, Adam or SGD. And then finally, for each batch, we compute and accumulate matrix. So for instance, matrix could be accuracy or MSE, etc. And then at the end, once we've trained for one epoch, we compute the loss and matrix on the validation data set. So what Poutyne does is actually it adds these callback here, where at the beginning and end of each epoch, there's the callbacks are called, and then at the beginning and end of each batch, again the callback are called, and also before optimizing, but after backpropagation, we callback to. So this is the approach that we take for training. One thing that you might have not noticed is that with this framework, you cannot train, for instance, YAN. This is the only thing actually the only kind of network that I see that you cannot train with Poutyne, but otherwise most like the majority of neural networks, you can train them that way. And then let's look at how we do evaluation of your neural network. So Poutyne contains evaluation metrics to do, for instance, early stopping. If you want to early stopping, for instance, when the validation accuracy stop increasing, then you can do that. And we also do checkpointing and logging of these evaluation metrics. So we have two kinds of metrics in Poutyne. The first kind are batch matrix. So batch matrix is essentially our decomposable matrix. For instance, accuracy, MSE. So a decomposable matrix is a matrix where you can take, for instance, for each batch, the accuracy, and then at the end of the epoch, you can do an average of your batch's accuracy to get the overall accuracy of your dataset. So, for instance, any PyTorch loss function are decomposable since they are all being of the example in a batch. The other kind of matrix that we have are epochs matrix, especially for non-decomposable matrix. So, for instance, F1 score or EUC-ROC are non-decomposable matrix where you cannot do an average of F1 score and still get the F1 score for the whole dataset. And so you can define your own epoch metric. You can also use a scikit-learn wrapper that we made so that, for instance, to compute the EUC-ROC, you can just pass the EUC-ROC of scikit-learn to this wrapper, which will compute the EUC-ROC for all your dataset. So here is an example of using matrix. So when you instantiate your model, you just pass here your batch matrix and your epoch matrix. Here I pass accuracy and F1 score. You can also define your own. Here I just pass string because they are predefined in Poutyne, but you can define your own batch matrix and epoch matrix. And then when training, your callbacks can act on these metrics as we see. And finally, when we evaluate, we also get, for instance, here the accuracy and the F1 score as a return of the evaluate generator method. So now let's look at callbacks. So here is the interface of the callback class. So essentially, this is the same as I showed you in the pseudocode, except there are a bit more methods. So we have on-epoch begin, on-epoch end, on-train batch begin, on-train batch end, on-backward end. And we also added recently on-test begin, on-test end, on-test batch begin, on-test batch end. So these methods here allows us to be called when training and to do actions. So for instance, here is an example of usage of callbacks. So for instance, if we look at the list of callbacks here, I put as an example, here the first one is a model checkpoint, which basically will save at the end of each epoch, it will save the weights of the neural networks into this file here that I called here last epoch.ckpt. There's another model checkpoint there. This I pass an option that is called save best only, which basically it will save the weights of the neural networks into the best epoch.ckpt when the validation accuracy increased from previously. So at the end of each epoch, this model checkpoint will check if the validation accuracy increased from previously, and if so, it will save the weights of the neural networks into this file. And finally, there's a CSV logger where it will save at the end of each epoch the statistics for the epoch. For instance, the validation loss, the training loss, validation loss, and the matrix, for instance, the validation accuracy, training accuracy, etc. And then what we have to do simply is to pass this list of callback into the training method here, fit generator there. So different kind of callbacks, we have different kind of callbacks in Poutyne. So the first kind are checkpointing callbacks. For instance, model checkpoint, as I just talked about. We have also optimizer checkpoints, which essentially can save the state of optimizer to, for instance, to be able to continue optimization from some point in time. And also LR scheduler checkpoint for a bit of the same thing, so that you can continue optimization after stopping it. We also have early stopping and LR scheduling callback. So early stopping essentially will look at some metric, and then it will stop optimization when this metric stops improving. We also have callbacks for any PyTorch LR scheduler. So PyTorch already provides a lot of learning rate scheduler. We simply wrap them into callbacks. And we also have fast AI like learning rate policies. So essentially, the library FastAI contains many learning rate policies that we integrated in Poutyne. We can also play with gradient. So for instance, we have this clip norm and clip grad callbacks, where essentially it wraps the PyTorch respective function. So you just add these callbacks into your list of callbacks, and it will do the clipping gradient. We also have TensorBoard gradient tracker, which essentially save running statistics from your gradient. So at the end of the epoch, you have statistics for the gradient of the corresponding epoch. So that's it for callbacks. Now let's talk about experiment. So experiment essentially wrap everything into a single class. Let's look at it. So basically, the experiment class, what it allows you to do is to stop and resume optimization at will. So for instance, you can train for 5 epochs, and then after 5 epochs, you can decide to train for 5 more epochs. So the experiment class will take care of this for you. It also saves and logs everything into a single directory. So if we look at the code below, you can see that we instantiate an experiment object, which we pass a directory with your neural network. And we also pass here some tasks. So the task here, for instance, classifier or regressor. So it could also be, you could also pass your own loss function and matrix, except that here task is a predefined values for those. So it can also simplify how quickly you set up your experiment. And then once you initialize your experiment, you just train and test, then this does everything I just described above. So essentially, the experiment class save the last checkpoint and every best checkpoint, as I showed you before. It also saves the last state of the optimizer and the learning rate scheduler. So it uses these callbacks. So when, for instance, you stop optimization and you want to continue, it just load back these checkpoints to resume optimization. And then finally, it logs training, validation, and validation loss matrix, validation loss and matrix into CSV and TensorBoard automatically. So this is it for the experiment class. So let's look at some library that exist already that are similar to Poutyne. There are a lot of libraries. I just took the most, I say similar, or because they all look almost the same, but I just took the most popular, I would say. So the first one that you might have heard of is PyTorch Lightning. So PyTorch Lightning is a really flexible library for training neural networks. One thing I don't like about PyTorch Lightning is that it couples the network with training. So with PyTorch Lightning, what you have to do when you define your network, you have to inherit your neural network from a special class, and then in your class you have to define, for instance, your data loader and your optimizer, your LR scheduler, and then and also define your neural networks. So this is not very nice in my opinion, because when you have a neural network, most of the time you want it to be independent. For instance, you want to change, for instance, the data that you train it on, or the data you train it on, or your optimizer, etc. So this removes flexibility from training. And finally, I just find that sometimes, since it's really flexible, sometimes PyTorch Lightning will add boilerplate where it shouldn't be. For instance, when defining optimizers with PyTorch Lightning, you have to define your LR schedulers. So when it's time to apply them, then it seemed very not complex but cumbersome to apply them. Whereas, for instance, in Poutyne, you just add them as callbacks, and then it simply works. Another library is the FastAI library, which, from what I've seen, offers a lot of features. But I also found that the FastAI library is not very intuitive. So I don't know if it is all the documentation is done, or maybe I'm just bad at at reading the documentation. But I had difficulties like finding like the pieces I needed to train my neural networks as I wanted to train it. And finally, there's LNLP. So I mentioned LNLP not because it's for NLP, but because LNLP has some kind of experiment framework that they call trainer. So this trainer is similar to the experiment framework, since it saves like everything into a directory, etc. But what I found is that in addition to being specialized to NLP, this trainer is not very flexible. For instance, the constructor of the init function contains like 30 parameters. So that's a lot of parameters for this constructor. So let's do a demo. So I chose here this data set, which is the Cub 200 dataset, which contains 200 bird species and contains 6,000 images. So what the demo will show you is that we will train ResNet architecture, pre-train ResNet architecture on this data set. So this is the Jupyter notebook I want to show you. So let's start by importing stuff. And then the first few cells are simply like loading dataset and splitting. So I already did the split train valid test. So I just skip it here. So then we choose which device we want to train on. Then some hyperparameters. So then we have here this set seeds functions, which is a function defined in Poutyne, which basically set the random seeds for Python, NumPy, and PyTorch, so that the training be as reproducible as possible. So let's do that. So we define the data loader. We define our neural networks. Then we freeze the weights of the neural networks, except for the last layer here that we change, because we want to fine tune only the last layer. So everything I just showed you there is just like usual PyTorch training. So defining your data, defining your hyperparameter, etc. So now let's look at Poutyne. So as in the slide, we defined callbacks. So the same 3 callbacks that we have in the slides. We define our model that we send to some device, then that we fit. So let's run it. So here you can see the output of Poutyne. So at for each batch, we output the loss and accuracy, since we define a batch metric as accuracy. And then at the end of the epoch, we will see that we will have the F1 score for training. So the F1 score for training, and we also have the validation loss and matrix. So validation loss, validation accuracy, and validation F1 score. The line that follows is simply one of the callbacks. So this is the callbacks that saves only the best checkpoint, which says to us that the validation accuracy improved from -infinite to 11. So, and then if we look at the end of epoch 2, then we see that here that validation improved from 11 to 21. So, yeah, so this is it for running code. Since this takes a lot of time, I just go in the notebook here that I saved. So essentially, you can see that sometimes it doesn't save checkpoints. Sometimes it saves them because it increased from the third before. And then at the end of the epoch, we test on our test set, and we have the accuracy and then the F1 score on the test set. And then since we save the results into CSV, we can load this CSV, and we can also, for instance, plot the loss and validation loss, and accuracy and validation accuracy. And then what we can do is simply load here the best model that we saved, and then again compute our matrix. So this is the same as before, because yeah, so here we also restored the best model. And then at the end, we have the experiment class. So essentially here, instead of defining callbacks, we initialize this experiment class where, and then we just train. When we call this method, we train for 5 epochs, and then we test. So, and let's say we see that the optimization has not finished for 5 epochs, then you can say train for 10 epochs instead. That is 5 more epochs. Then Poutyne will load the weights from the neural network and from the optimizer, and then it will train for 5 other epochs starting at epoch 6. And then at the end, we can test again, then we can see that the test accuracy improved. So that's it for the demo. Here is some future work that I want to talk about. The first one is simply a question of aesthetic. That is, we want to use TQDM, which is some library for progress bar. So as you've seen in the demo, there is not really a progress bar, simply like a step I over n. Here, I want to add a progress bar to be able to have a more visual feeling. And then we also want to add colors. So for instance, maybe colors the training matrix differently than the validation matrix. And then the same thing for other information that we display. Also, the second one is more of a documentation right now, the Poutyne documentation has examples into, for instance, in the model class documentation, we have examples, but I want to make a web page where you have a lot of use cases where you can find what you need to do. I also want to integrate multi-GPU support. So right now, you can train with multi-GPU, except that you have to do it in your own neural networks. What I want to do with Poutyne is to integrate this multi-GPU support so that you can just say, I want to train on these 5 GPUs, and it will just do it. And finally, these two other points are maybe more functionalities. For instance, adding easier way to add a regularizer and easier way to initialize the neural network. And finally, I want to integrate an experiment library such as, for instance, MLflow or Sacred that will say, for instance, the hyperparameters or your code that you're running, so that you can find which code you ran when you obtain which result. So this is information to get Poutyne. So we can install it using pip. And we also have a website, poutyne.org, and the code is on the Graal Research organization on GitHub. So this is the website. And as you can see, there's an image of Poutyne and with some description of why we chose the name. Maybe I'll just let you read this description. And we also have Jupyter notebooks, the one that I showed during the demo, and we have a few other notebooks as well. And the library is under license LGPL v3, so you can contribute, and we have contribution guidelines on GitHub. So yeah, one last thing I wanted to say here is that Poutyne is in the PyTorch ecosystem webpage on the PyTorch website. So if you go on pytorch.org/ecosystem, you get Poutyne is listed there. So that's it for me. Thank you for listening.
Thank you, Frédéric, for your presentation. Maybe I would say it's good to precise on the web page that it is for the Putin, because otherwise people may think about an authoritarian government leader instead of the meal. So I think they may think that we will face, because it is written as Putin, as people are used to write it in English. Anyway,
no, but in English there's no O in Putin.
Okay, it's really Putin. Okay, right. Okay, so it's the Putin in French.
Yeah.
Okay, yeah, that's right. Anyway, anyway, it's good to be to get the meaning right. So I don't know if there are any questions from the people who attended the presentation. No question yet. I have one. I think you talked a little about it when you presented at the end as extensions, but how about multi-GPU? Because for me, multi-GPU is one of the difficult things to do right now when you want to train big neural networks. How do you see the integration of that into Poutyne?
So yeah, I mean, like right now, what PyTorch offers is simply like it splits a batch into like multi GPU. So let's say you have a batch of 64, then and you have 2 GPUs, and we will split 32, 32. So you get 32 examples on one batch and 32 on one GPU, and 32 examples on another GPU. And then at the end, it's just like it's just like averaging the gradient to get the right result.
Mm-hmm.
So essentially, in Poutyne, what you want to do is to integrate this mechanism of PyTorch into Poutyne directly instead of having to do it outside of Poutyne.
Okay, so you will just only kind of encapsulate the data parallelism mechanism of PyTorch.
Yes.
Okay, because I think that, you know, I'm just talking because that's something that kind of I look at this in fact today previously. It's just that it's difficult to deal with multiple GPUs, while, you know, often when you are facing systems with many neural networks, maybe that are kind of collaborating. Just again, you have two neural networks, so you have the generator and the discriminator, and sometimes you face memory issues and so on. So I would say, how can we deal with that in, I would say, relatively easy high-level view, because everything is doable, but the level of complexity may vary. So I was wondering if you are looking, so for now you are looking mostly to split the batches in smaller batches on each GPUs, right?
Yeah, I mean, like, if your network is too big that it cannot have simply one example in it, then maybe you have a problem with your architecture. I don't know. Like, in my opinion, if you're not able to get at least one example on for your network on your GPU of 8 gigs of RAMs or 12, maybe you have some problem with it. I've heard of the new, I don't know, BERT model, or I don't know how they called it, but like it has like a 100 billion of parameters. I don't know, like it's not very future-proof way of doing neural networks if only a few people can run them, can train them like at home.
Yes, of course, you need to get like a big GPUs with 24 gigs or 32 gigs, and even with like NVLinks that will will share the memory between many GPUs. But still, I agree that it's good to consider first to have it to fit within memory. But one thing I see is that when you do complex systems, you may have many networks, and then, you know, it's just not just that your network is too big, it's that you have many big networks, so that may be difficult to handle. But that may be relatively specific still. But well, you know, more and more we have architectures with 2, 3, 4 networks that are trained together or doing something together. We have a question from
maybe Christian.
Yeah.
If any one of your lab want to contribute to improve the Poutyne in this direction, they are welcome. And there are some the possibility that there are some funding for their work. So
nice. I don't know if I would say it's more a question I'm asking myself about how to deal with big networks. So far, the students were able to play around it, but it is not necessarily easy. But yeah, maybe if we look at a more systematic general approach to solve that, that may be interesting.
Yeah, and to have your point of view of AutoML also might be interesting.
Yes, if you want to tune many, the hypers on many, yeah, I will think about it. Thanks. I know we have a question from Michael Gelina. He wrote, I'm curious about what would be the best use case scenario and the worst case scenario, use case scenario to use or not to use Poutyne. So Frédéric, maybe you can comment on that.
Okay, so the best use cases are actually like classification or regression network that are vanilla. I won't say like let's say you have, for instance, image classification where you output a classification and then you have your crescent entropy loss. Then this is really easy to use. Worst case scenario essentially are GANs, where GANs you have multiple optimizer, you have multiple optimizers. So this is something that is not supported yet. Maybe I was thinking of something, adding some kind of setup class where you could define like all the optimizing step is done, but this is not something you can do currently. And then everything in the middle, I mean, like I train like variational autoencoder, domain identification network where you have like, for instance, reverse gradient and etc. You can do all that with Poutyne. But this is just a question of when you have stuff like that, then this is a question of splitting your training into like this essentially this scheme where you compute some result, you apply some loss function, and then you do the backpropagation. So yeah.
Thank you. I don't know, is there any other questions? Seems not, but I would say, in fact, maybe that's the GAN thing, and maybe like I would say, especially in computer vision, where we are like dealing with multiple losses, multiple networks that are like organized into some kind of GAN-like, or with many losses with different treatment. I think this is a more and more common when you're doing applied stuff.
But I mean, yeah, like usually, even if you have like multiple losses, then you can usually just sum them and then just do the backprop on them. Where it blocks is where you have GANs with multiple optimizers.
Mm-hmm.
But if you have multiple losses, then you're fine. You can just fit all your losses into one loss function that will do like the addition of your multiple losses. But when you have multiple optimizer, that's when you cannot do it.
Yeah, because the control flow is kind of split between the different optimizers. Yeah, that's a matter of the control flow. Okay. Interesting. So thank you, Frédéric. And there was a question about Thierry Badard, who said, "Is there will be able to get the slides?"
Yeah, sure. I can send them to you, Christian.
Mm-hmm.
And also I will probably put them on the Poutyne website or something like that.
But you know, okay, so we recorded the video. I don't know if you want to publish it, but one thing we can do.
Yeah.
So I think the best place will be we'll put everything into the IID Google group. So we'll just maybe, I will send you the video, Frédéric, but maybe one thing will be to post the slides plus the link to the video on the IID Google group, so everyone interested can get the link.
Yeah, sure.
Great. Okay, thank you very much.
Thank you very much.
Bye-bye.
Bye-bye tout le monde. Au revoir, Fred.